now for the main event. Our first guest speaker tonight is Dr. Jeffrey Hall. He's the director of the Lowell Observatory. He has a BA in physics from Johns Hopkins and a PhD in astronomy and astrophysics from Penn State. He joined the staff at Lowell in '92 as a postdoctoral research fellow, specializing in variations of the sun and sun-like stars, lending an astronomical perspective to solar effects on terrestrial climate. His principal avocation is music. He is the substitute organist at Epiphany Episcopal Church in Flagstaff and former president of the board of directors of the Flagstaff Symphony Orchestra. It's all right. Presently, he is the chair of the American Astronomical Society and a standing committee on light pollution, radio interference, and space debris. Dr. Hall.
Okay, thanks very much. Really pleased to be here. Thanks for having me down and for taking the initiative to look at dark sky city status. As Bruce alluded, I'm going to start with a little bit on why we are interested in dark skies, why we want to preserve them, and how in general to do them. I'll talk about some of the basic principles for how you do good lighting and preserve dark skies, and then use what we've been doing in Flagstaff as an example of how to achieve that. And then after me, John Barentine will be going much more into the specifics of how to get IDA dark sky community status. So this is a fairly natural dark sky taken from near Flagstaff. You know, in the absence of excessive artificial night at light, the sky over Phoenix could look like this. You'd have to replace the pine trees with saguaros, I think, but you know, this is what we're missing. And the night sky has been a source of connection and storytelling and tradition and discovery for tens of thousands of years for humans across the planet. So it is a valuable and worthwhile resource to preserve. So let's look at a little bit at what we've got now. This is an image from the International Space Station of the Earth at night these days. And you're looking here at the eastern United States. Right there you can see the entire outline of Lake Michigan, right? This is the Chicago Metro going up to Milwaukee, Indianapolis, St. Louis. This is going to be the Minneapolis area here. You can see the patterns of civilization almost everywhere. You know, the straight lines where in the Midwest everything becomes very square, and then more striated light patterns over there. Coming a little closer to home, we have an International Space Station image of the West. And here you can see the Valley of the Sun. There's the Phoenix Metro right there, I-10 going down to Tucson, I-17, and then right up here, we can see all of our communities, right? There's little Flagstaff right up there, and Sedona, and Cottonwood, Camp Verde, Prescott. And then all the way over, this is I-8 coming over to San Diego, and then, of course, up here, Las Vegas. Trying to be as bright as it possibly can, but I mean, but look at the image. You can see community decisions on this image, right? Las Vegas is almost an unbroken glare bomb. Phoenix, fairly intense, but now look at Tucson. You know, much smaller than Phoenix, but still a substantial metro. But Tucson, for decades, has been working very assiduously on preserving dark skies through good lighting practice because of the concentration of observatories right around it. And you can see the difference, right? And so it can be done even in major metro areas. And so having Cave Creek considering dark sky status here on the edge of a major metro area is a very good thing. So now we can look on a slightly more global level. I'm just trying to give you a picture of the status of the world right now. This is from a recent atlas of light pollution. Basically, any place that's not the dark gray has an elevated sky brightness. So what you can see here in the eastern United States, anything east of a line going through about Dallas and Minneapolis, there's basically no natural dark sky left. One of the first things that disappears when the sky brightens up is the Milky Way galaxy. We can see the Milky Way galaxy from downtown Flagstaff, and you can see it here too with good lighting practice. Obviously, Europe is quite bright. You can see China, Japan, South Korea is quite bright. Zooming in on the United States, you'll see, again, basically nothing left east of about 100 degrees longitude or so. And even in the West, these dark areas of fairly natural dark sky are becoming increasingly far and few between. One of those is northern Arizona. Flagstaff is right in here. There are some natural dark sky areas left, but they're rapidly declining. And it's estimated now something like 3/4 of the world's population lives where you can no longer see the Milky Way and no longer experience that connection to our ancestry. So what exactly do we lose when we lose dark skies? So I'll talk about a couple of the motivations for preserving dark skies. I'll start with astronomy since I am an astronomer. And we'll just talk about a couple of sites that are up there and some of the stories associated with them. This is the constellation Orion. After the talk tonight, I cannot go outside and show it to you because it's down there. This is a wintertime constellation. One of the most distinctive constellations in the sky. It has an unusual number of very bright stars. These are extremely massive, luminous stars. I'm going to date myself a little bit, but sometimes I call these stars the John Belushis of the universe. They live hard and die young. They don't last very young. In fact, in a mere 2 million years, which is almost nothing celestially speaking, this will basically be gone. All of those stars will have exhausted their fuel and pretty much exploded. You can notice several things here. There's a very red star there. That's the star Betelgeuse up in Orion's shoulder. There's the stars of his belt, and the brilliant blue-white star Rigel. This is a stellar thermometer. The stars here are telling us something about their physics. The red ones are very, very cool, and these white ones are extremely hot, up to 10 or as much as 20 times hotter than the sun. But in addition to these very bright stars, there are things hidden in every constellation in the sky, like that little smudge right there. It doesn't look like much to the eye, but when you put NASA's Hubble Space Telescope on it, it turns out to be that. That's the Orion Nebula, which is a stellar nursery. Right here is basically a birthplace where new stars and new light and new warmth is joining the galaxy. Stars come and go in generations. This is one of the places where they're born. So that's kind of the astronomy of Orion, but for tens of thousands of years, the skies and the stars have been sources of stories. Orion, in Greek mythology, was a very proud and very strong and very assertive hunter. And if you're in Greek mythology and you're a proud, confident hunter, one of the things you do is PO the gods. Like they say in the Geico commercials, it's just what you do. And then the gods get mad, and they decide to put you in your place. So in Orion's case, long story short, he did some untoward things, and they sent a giant scorpion to dispatch him, which it did. And then Zeus set him in the sky. Now, the scorpion, I could show you after the talk tonight. This is Scorpius. Here his claws are right up here, and then his body curls down this way, big curving body like a scorpion, and right there is the stinger. And that's out in the southern skies directly over the beautiful glow of Phoenix. If we could actually see it, it would be visible tonight. You see one of these very red stars amidst the white ones. You see the center of the Milky Way galaxy. This is looking to the very core of our galaxy. You can see a huge cloud of stars, gas and dust. Scorpius is a summer constellation, and the idea there is when the gods put the Scorpion and Orion in the sky, they knew they were mortal enemies, so they put them at opposite ends of the sky. So when Scorpius is rising in the summer, you will see Orion departing as fast as he can in the other direction, setting in the west. Now, right next to this huge red star Antares is a little tiny smudge. Again, look at that field. That's just one little smudge. It turns out to be this. It's actually a cluster of about 500,000 stars. Ancient systems that provide clues to the history and the formation and the evolution of our galaxy. They're satellites of our galaxy, probably about 10 billion years old. These things are the first things to go astronomically when we brighten up the sky. But there are many issues associated with dark skies that go well beyond astronomy. One of them is ecological. Any number of different species of plants and animals rely on the natural cycle of light and dark. in the case of animals, for reproduction, for navigation. Sea turtles, when they hatch, have to get to the ocean, and they use light glinting off the water to orient themselves. If there are bright lights ashore, they get disoriented and go the wrong way. There are ways to address that with sort of turtle-friendly dark sky lighting. Not difficult to implement, and many places have done so. So there are serious ecological consequences to losing the natural cycle of light and dark. Another one that I've been directly involved with is this one. This is a little screenshot from an email I got last summer. You can see, "Dear Jeffrey Hall, time to fill out your online 2018 cancer prevention study." So I've been doing this for about 15 years. They just emailed people to see who wanted to participate. So I said, fine. This is the Centers for Disease Control. Basically what they do is every 3 years they send the whole survey sample, a big online survey, and they're asking questions about your lifestyle, your diet, exercise, what are your habits. Clearly what they're trying to do is collect information from a large set of people and look for either risk factors for various types of cancers or things that seem to be a healthier lifestyle. So in the most recent one in 2018, there was a whole new section in it asking me about my daily exposure to light. And it was not just a throwaway. It was a very detailed section. They wanted to know, are there lights in my bedroom, like night lights or bright clocks? What times of the day am I out under natural light? Am I under artificial light? What kind of artificial light? There's not, the data here are not ironclad, but there's increasing thought that the gradual brightening of the night and the gradual loss of the natural light-dark cycle may have significant health impacts. And, it doesn't seem unreasonable given that as humans, we've gone for perhaps a few million years with completely natural cycles of light and dark, and suddenly we have a great deal, since the Industrial Revolution, a great deal of artificial light at night. So the medical community is definitely very alert to the issue of dark sky protection and its possible impacts on human health. So there's a myriad of reasons to try to do this beyond just enjoying the beauty of the night sky, although for me that's certainly a big one. I love to go out and look at the sky. And of course, when you come back to astronomy, it's one of Arizona's major industries. There are lots of observatories around Tucson. Lowell is not the only observatory around Flagstaff. There's well over $1 billion of capital investment in the state, and dark skies are vital to that mission. So that's a little bit about the why. So let me transfer now into a little bit of the how. And I'm going to talk about the key items you need to think about in doing good lighting and dark sky protection, and then how we've implemented it in Flagstaff. And we were the very first international dark sky city, having received that designation from the IDA in 2001. There are now 4 other, so Sedona, the Village of Oak Creek, Camp Verde, and most recently, Fountain Hills. You got them all? Yep. So that's 5. Cave Creek would be the 6th, and there are only, how many worldwide in the communities? 22. 22 worldwide, and so it would be 23 worldwide, 6 of them right here in Arizona, which would be quite something. So this slide shows basically the three critical legs of the stool in dark sky protection and how they're implemented in Flagstaff. So one of them is fully shielded lights. We'll talk about that in just a second. So that all of the light is being directed downward. None of it going up. It's all coming out below the horizontal. The second is illumination limits. So basically you set limits on how many lumens you can put within a given area, say per acre. And this is a parking lot that has to comply with that. You can see it's perfectly well illuminated. You can see from one side to the other, and yet it's at a fairly subdued level. And then the third one, which I'll take a little bit of time to explain in some detail, is managing the spectrum, or the color content of the light that's being emitted. In this picture, you can see one of the hallmarks of Flagstaff's lighting, which is very narrow spectrum amber light. And so these fixtures right here are what we call low pressure sodium fixtures. It's essentially a monochromatic, almost just one wavelength of light being emitted. And if you think about it, that leaves the rest of the spectrum completely untouched. I'll show you that in a couple of slides. Okay, so to sort of go into a little more detail on those three legs of the stool, the first one here, full cutoff shielding. This is a diagram from the Flagstaff City Ordinance, just providing some examples for people reading the code of what qualifies as a fully cutoff light. And you can see here sort of intuitively, any of these fixtures would not emit any light above the horizontal. Some of them here are residential. Some of them are more commercial. This is one of the very common Cobra head fixtures that you see in use in street lighting systems all over the place. That is what those are often what we call high pressure sodium light. That's one of the standards worldwide. If you take a commercial flight at night and you look down and you see the sort of yellowish straw yellow glow of the cities below, that's what you're seeing there is mostly the high pressure sodium emission. That's all changing very rapidly, and we'll come back to that in a little bit. So this is something that's absolutely simple. Any community can adopt this. Any business, at the community level, any individual at a residence, installing fully shielded lighting is trivial and all by itself would go a long way if implemented worldwide to reducing sky glow. Illumination limits. This is another diagram from the Flagstaff Code. We have defined 3 different zones within the city. Cave Creek very well might not need to do this, but from 1 to 2 to 3, they become progressively less restrictive. In other words, you can have a little more light out here than here. The reason for that is just to the west of Flagstaff, right at about here, is the field station of the United States Naval Observatory. It's the other major observatory in Flagstaff, and they have major research telescopes right on site, about 4 miles from city limits. So they, whoops, let's see here, hit the wrong button. So they put the most restrictive zone over here, and then zone 2 a little less, and zone 3 even less so as it's farther away. Lowell Observatory, our main campus, is right there in zone 2, but at our campus we mostly use it in our public outreach programs, and we don't need quite the level of dark skies you do for a major research telescope. Our major telescopes are out southeast of town at Anderson Mesa, and the new big one right above Happy Jack. That's our new 4-meter telescope. It was a cool little $53 million toy that's going to ensure our research competitiveness for the next several decades to come. That telescope is called the Discovery Channel Telescope, which will give you a little clue as to who gave us a lead gift to help build it. It's like the Chase Field of telescopes. They gave us a $16 million gift to kickstart the project. They got naming rights and first rights to use images from the telescope in their educational programming, but it was a gift. They don't own it. They don't control what we do with it. It was all around a very nice deal. So that's way out here down Lake Mary Road. But anyway, installing or setting good illumination limits, that's certainly something the IDA can help you determine what makes sense and what's good. And then finally, the third leg of the stool is the spectrum protection. And this is something we've paid very close attention to in Flagstaff. It's often overlooked, but it's really important. So what I've got here are the spectra of different kinds of outdoor lights. And basically, I mean, you've all gotten a little prism from a department or a store, and you put the little bar of sunlight on the wall. That's what you're seeing here. This is just the spectrum of colors that we can see sort of from indigo over to red. And here are the spectra of different kinds of lights that are in use or have been in use. To oversimplify things a bit, basically, the broader the spectrum of the emitter, the broader the range of colors that emitter is creating, the worse of a dark sky light it is. It's a little bit oversimplified, but it's one of the essential points. So what we have here, you can see why Flagstaff, with $250 million of observatory assets right around its city limits, has gone for the absolute highest possible standard, which is low pressure sodium. And as you can see, low pressure sodium emits just at this basically one wavelength. There's a few others, but that's basically it. It looks amber to the light. It leaves the rest of the spectrum completely black. This is one of the reasons, right from downtown Flagstaff, the Milky Way just pops out of the sky, because there's none of this other emission in there. It's critical for astronomy. It also makes a difference to visual appreciation of the night sky. Problem: low pressure sodium has now officially gone the way of the dodo. It's been discontinued. Basically, it's a supply and demand issue. Nobody uses it, and the new wave of LEDs is basically taking over. There's just a revolution in lighting, and everyone is switching from the legacy systems of low pressure sodium and high pressure sodium to LED. So you can see low pressure sodium is outstanding. HPS, not too bad. So these are those Cobra headlights that have kind of that straw yellow color. What's happening around the world today, including in Phoenix, including in Tucson, including in Flagstaff, everyone is switching out these to these. These are white LEDs. You'll see them all over Phoenix, see them all over Tucson. They come in different flavors. We'll talk about that in a minute, but you can see that compared with the old metal halide, which is just about the most abominable thing that's ever been created, the white LEDs are extremely broadband emitters, and importantly, they have an extremely high concentration of blue light. They're very blue rich. Blue light is, your eyes are sensitive to blue light when it gets dark. That's where the sort of the glare, the very harsh look of the white LEDs comes from. There are ways around it. You can filter that out. You can put filters over the LED to knock out the blue. But still, even if you do that, compare that spectrum to this one. So lumen for lumen, if a town switches out, if you have a street light system that's entirely high pressure sodium, if you switch it out to filtered or white LEDs and just maintain the total light output, you will increase the sky glow by about at least a factor of 2, maybe closer to 3. Over the low pressure sodium factor, it will go up by a factor of 6 to 8. It's really quite dramatic. So what are we going to do here? I'll give you some examples of what we are doing right now in Flagstaff. The observatories, we've been working very closely with the city to come up with a solution. You know, because we're mostly low pressure sodium, and they're in a rock and a hard place. Nobody's making it anymore, so we're going to have to make a switch. Flagstaff has an outstanding commitment to dark skies. The first dark sky ordinance was put into place in 1958, so we have a 61-year tradition now, and we've been working with the city. And this is an example of the good, of the bad, the not so bad, and the really good. So white LEDs look like this. I took this from a parking lot of a highly a bunch of evil miscreants, and I will leave them unnamed. It's a large big box store. I drove by one night, and they just switched out their low pressure sodium and said, "Oh, white LEDs." These are actually 5,000 degree white LEDs, and they are absolutely horrendous. And it took us over a year and lots of foot dragging to get them to switch it out. But this is an absolute non-starter. If Phoenix were to go to this, Phoenix is not, the light dome over Phoenix would increase dramatically. Filtered LEDs look a bit like this. I took this picture in a parking lot in Hilo, Hawaii. And what they've done here is taken these very high temperature white LEDs and put a filter on the fixture that knocks out the blue light. And what's left is this sort of green color. Now, speaking not as a dark sky advocate, but just as a citizen, this is an example of the lights. We had several of us. We went out over there, and we were all green. And it was like the zombie apocalypse. And as a citizen, I think these things are just hideous. Oops. Outlook will not be deterred when it wants to do something. So there are ways to use filtered LEDs that produce a more pleasing color. You can use a lower temperature white LED that produces more of a straw color. But there's an even better answer, and here it is. And here I get to use a picture that John actually took, which I forget where oh, you tweeted it. That's what it was. That's where I found it. So there are other kinds of LEDs that much more closely replicate the better kinds of dark sky lights. What we are going to be installing in Flagstaff are narrow band amber, and this is the parking lot of the new Marriott Hotel right across from City Hall. It's an exemplary example. Look at the nice uniformity of the lighting on the parking lot. This is a very narrow spectrum LED. It doesn't touch very much of the spectrum at all. It is the best possible answer to any sort of switch from an older system. The trade-off is the narrow band amber fixtures are more expensive to buy, and they're a little less, well, considerably less efficient to operate. You just get fewer, you get less light out per watt that you put in than you do with other fixtures. So this is also an extremely strict standard. Many communities might not need this, but there are, with such a concentration of research observatories right on the boundaries of Flagstaff, it's important for us. There's another answer that not a lot of folks know about. This is a picture that John took. I think this was over in Las Cruces. Yeah, Mesilla, New Mexico. And these are phosphor-converted amber LEDs. Right now, these are almost as good as white in terms of efficiency and cost effectiveness, and yet they're a much narrower spectrum. So in Flagstaff, we are going to be using a mix of narrowband amber and phosphor-converted amber. Those put out a little more light, and the city wants to use phosphor-converted amber where our infrastructure doesn't quite allow the NBAs to work. That's a bit of a compromise because these are broader spectrum emitters, but you know, getting these things done is all about compromise. So the new Flagstaff standard will be narrowband amber, period, with phosphor-converted amber as a stopgap where things like pole spacing and infrastructure requires that we use it. So going back to our spectrum picture, basically, the narrowband amber is an answer to low-pressure sodium. I do not expect NBA to be adopted widely by communities that don't have giant observatories right next to them. And frankly, for a community that really has to balance dark sky protection with economic reality, this might not work. PCA, however, is a really viable option that, as far as I can tell, very few people know about. Not even my colleagues in astronomy. I'll mention phosphor-converted amber to them, and they're like, what? So nobody seems to know about it, but it's a really good answer. So basically, as we switch to LEDs, white LED of any temperature, the high-temperature white LEDs are those incredibly blue-white ones. You can get lower-temperature ones. So Tucson, for example, is using only 3,000-degree LEDs. Phoenix, thanks to some hard work by dark sky advocates locally, is adopted 2,700 degree. But the thing to remember, even those lower temperature whites will still increase the sky glow over high pressure sodium by a factor of about 2, unless you also do what Tucson did. So in switching from their old street light system of high pressure sodium to the new LED system, they have these much brighter, glarier lights, but they also chopped their total illumination count, lumen count down. So previously it was about 480 million, and they cut it by about 2/3. And so you have switching to the white LEDs, bad, cutting the total light output, good, and they roughly preserved the sky glow. You know, it's one of the reasons Tucson looks good in that satellite image. We'll be doing the same thing in Flagstaff, except even notching it one step further. We're going to switch to the narrowband and PC amber, and our total streetlight lumen count will go from about 27 million to about 21 million. The reason you can do that, there are compelling reasons to switch to LED. You can point them where you want. You know, high pressure sodium, low pressure sodium light, it just comes out, it goes where it's going to go, like onto people's yards. That's light trespass, or you have a big light in your window. LEDs, you can point them right onto the street, so you don't even need that light. You can cut your energy usage, cut your total illumination, put it right on the ground where you want. LEDs are not the enemy. They just can be ruinous to dark skies if they're not implemented thoughtfully. So we will not be using whites. Narrowband amber, I would always advocate if a community really wants to just jump in the deep end with dark sky protection, you can do that, but you're going to pay a price for it. But everybody should keep PCA in mind as a very nice, pleasant amber color. It's broader spectrum, so you'll have good color rendition. It produces more light. So if there are places where you want slightly higher illumination for visibility, for color, for safety purposes, you can do that. This is exactly what we're doing in Flagstaff, and it's making a lot of sense. To show you what can be achieved, here's an all-sky image. This is literally the entire sky, taken by a fellow named Dan Dorisco, who's retired from the National Park Service, showing the sky brightness. He took this from a point really close to Meteor Crater, and you can just see what can be achieved if you really pay attention to your dark sky efforts. So here's the whole sky. Basically, the bluer it is, the darker the sky. The green, the yellow, the red are where the light pollution is getting really bad. So you can see Phoenix clearly from all the way up by Interstate 40, about 115 to 150 miles away across the valley. 4.6 million people, so yeah, we accept this is a really big place, and there's just a lot of light. What I'd like to point out is Winslow, population 10,000, 20 miles away. There's the light dome. Flagstaff, population 75,000, and not a lot farther away. Much smaller light dome. That's what you can do when you apply those three legs of the stool. There are other sources of light. This is the rest stop out west of Winslow. Nice bright lights at the rest stop. And then there's light you want to see. There's the Milky Way, right there, stretching across the sky. So you can really, so the point here is you can make a community-wide difference. And I think it's really significant. This is the sky over Flagstaff. This particular view over Flagstaff tonight is sadly not quite nearly as attractive because that's looking right up to where the museum fire is currently burning. We're kind of crossing our fingers. And man, I was watching that Sunday afternoon and just overwhelmed by the professionalism of the air crews. It's just amazing how they bring 12 planes in there and they're going every which way and banking that DC-10 out of there like it's a Cessna, and props to them. So this is what we can achieve, and I think it's what we can achieve here. The Cave Creek being potentially the second community, what starts to rattle around my brain is, well, then who would be the third, and who might be the fourth? I think if we are bold enough to think of Phoenix as perhaps America's first dark sky metro, it's going to start at the community level. It's a real pleasure to come down here. I never know what to expect, but apparently we have connections here. I met Jill Hall, who went to college with Brian Skiff, who is an institution at Lowell. And where's Martha Arnold? Is she around somewhere? Oh, in the back. I met Martha, and Martha's dear friend Diane Blackett and Robert Wachs left Lowell a magnificent bequest, a parcel of land that's going to serve as our telescope operator and astronomer quarters about a mile from the Happy Jack telescope. It's going to enable us to sell the property, and the proceeds from that I'm going to put into our endowment in Diane and Robert's honor. And so thank you very much. That's a lovely... And we really rely on individuals like that as a nonprofit to help us keep our mission going. But we also rely on both communities and the state to invest and be part of this incredible astronomical enterprise we have going here. At Lowell Observatory, we have an outreach program. Invite you to come take part of that. We have over 100,000 visitors a year. It's going to be going up from that. We love to sort of share back all of these wonders that we're discovering, and we can do that because the state has these gorgeous dark skies that we are all invested in protecting. So thank you ever so much for listening and for your interest. I really appreciate your consideration. I'll be happy to answer any questions either now or after John's talk, however you want to handle it. Thanks so much.